Collins' English Dictionary defines marine science as the branch of science concerned with the sea. While it's easy to understand this oversimplification in the interests of the casual inquirer, the implication that the field of study is restricted to the ocean is misleading, as the physical characteristics of the ocean are inextricably linked with the many atmospheric processes which shape the Earth's climate and weather patterns. It's important to appreciate these connections and to understand how atmospheric features are not only mirrored in the oceans, but also influence their behaviour, and vice versa. In the same way that all life on Earth is dependent upon the Sun, all atmospheric and physical processes on Earth are also rooted in its influence. Its interaction with the Earth's atmosphere is key to this. The atmosphere is a thin, multi-layered blanket of gases wrapped around the Earth which protects it from much of the Sun's radiation, while allowing enough to penetrate to warm the planet and trapping re-radiated heat inside like a greenhouse. It also supplies the essential gases for life's processes, oxygen and carbon dioxide, close to the Earth's surface. These are kept in place by gravity, and this interaction is the basis for the air density and pressure systems which we'll look at next. Gravity pulls air molecules down, so the greater the volume of air above, the greater the compression, or pressure, on the air below. For this reason, high pressure systems are associated with low, dense air, while thinner, higher air creates low pressure systems. Gravity is a pretty constant force, so why are pressure systems not constant? Around 70% of the solar radiation, called insolation, received into the atmosphere is either absorbed by the Earth's surface or by the atmosphere itself, or bounces off the Earth's surface and is reflected back down by clouds. Once absorbed, this shortwave radiation received as light changes wavelength and becomes longwave as thermal energy, warming the air. Due to the spherical nature of the Earth, the amount of insolation received is not uniform across the planet, with equatorial regions consistently receiving greater amounts, while the tilt of the Earth means that in more northerly and southerly regions this fluctuates throughout the year, giving rise to the seasons and their associated weather patterns. For example, surface heating plays a significant role in the summer monsoons of Southeast Asia. Air density is largely dictated by temperature, with warm air being less dense due to expansion. In addition, the concept of pressure gradient force dictates that air will naturally travel from areas of high pressure to areas of low pressure. At the equator, therefore, where insolation and thus air temperatures are highest, warm air rises to higher areas of low pressure, where it cools, travelling away from the equator as it becomes denser, then sinking back down and cycling back towards the low pressure of the equator. This results in a cycle, or cell, of air current, and is replicated in cell sets to the north and south of the equator, known progressively as Hadley, Ferrel and polar cells. Air currents, or winds, created by these pressure cells understandably begin in northward and southward directions. However, the Earth's rotation causes deflection, bringing dominant easterly trade winds under Hadley cells towards the equator, while the reverse occurs under Ferrel cells at higher latitudes. The phenomenon causing this deflection is known as the Coriolis effect. Brief diversion. The Coriolis effect is an apparent force relative to the observer's frame of reference which causes an object leaving the Earth's surface to appear to curve to the right in the northern hemisphere and the left in the southern hemisphere. This is caused by the anti-clockwise rotation of the Earth, which effectively moves from underneath the object in motion. For example, a plane flying directly south from the North Pole toward New York would in fact land in Michigan. On Earth this would appear to have curved, but if observed from space where the Earth's rotation can be seen, the true straight path would be observed, so winds heading toward the equator in both hemispheres appear to deflect to the west. Although air pressure systems at sea level usually have minimal variations, it can't be said that they have similarly little impact on ocean processes. Friction caused by wind movement across the ocean, known as wind stress, pulls surface waters, which in turn drives surface currents like those seen in the air. Ocean currents, however, do not directly reflect air currents, instead forming circular patterns such as the North Atlantic gyre. Here, again, the Coriolis effect comes into play, deflecting westerly winds down through surface waters at an angle of around 45 degrees. As momentum transfers energy through the ocean layers, this effect is replicated, with each layer rotating further to the right until the current is moving at a right angle to the surface wind. This is known as the Ekman spiral, and explains how ocean currents as deep as 100 metres are dictated by atmospheric processes. However, in a mirroring action, this can also be observed in atmospheric currents, for example at Dome Sea in Antarctica. When sea level pressure systems do change, the effects are huge, as most famously observed across the Pacific. Generally, warm surface waters are blown from South America by trade winds, allowing upwellings of nutrients as cooler waters rise to replace them. Periodically, however, in an El Niño year, the trade winds die down, resulting in high atmospheric pressure and droughts in the West Pacific. Warm waters remaining around South America prevent upwellings, reducing the productivity of the ocean and in severe periods causing the collapse of the food chain. The warm waters then heat the air, which is driven northward, producing tornadoes in the US. When air pressure changes again, bringing the return of the trade winds, this effect is reversed with the emergence of La Niña, and many oceanic anomalies throughout the Pacific region are believed to be dependent upon the interplay between this cyclical phenomenon, known as southern oscillation, and the atmospheric response to it. As we've seen, wind drives currents in the surface waters, which account for around the top 400 metres of ocean water. However, wind doesn't affect deep water currents, so what drives these? In the same way that air currents are driven by air density, deep water currents are driven by water density. Again dependent upon temperature, the density of water is also contributed to by salinity, and the main current circulating the deep waters of all the Earth's oceans is the thermohaline, or Great Ocean Conveyor. To begin this cycle, we look to the Arctic Ocean, where warm Gulf Stream waters are cooled and become saltier as surface waters freeze, leaving their salt behind in greater concentration. This causes the water to become dense and sink, where it's known as North Atlantic deep water, and to begin its journey around the globe. Travelling south, the current meets with Antarctic bottom water, which has undergone the same process, and travels east before warming and rising in the Pacific Ocean to flow west through the Indian Ocean and eventually back up to rejoin the Gulf Stream. While the thermohaline conveyor is thought to take around 1,200 years to complete its journey, travelling slowly and largely unobserved, on the surface, waves are a much more visible example of the constant movement of the ocean. Created by the vertical transfer of energy from wind to the ocean's surface, these can translate minor pressure fluctuations into huge horizontal energy transfers. We saw earlier that wind blowing across the ocean carries surface waters with it, and this friction, known as geostrophic flow, is the foundation for wave building. As the water particles are carried along, they don't move directly forward but in a circular motion, transferring their energy forward with the wave crest before sinking back and being drawn up again by the next wave. This loop creates a small reverse wind, or eddy, which generates a rougher surface for the wind to catch. So the longer the wind blows, the more cycles occur and the more energy is transferred. Of course, the wind only has opportunity to carry waves as far as the fetch, which is simply the length of the uninterrupted stretch of water. And this is the other factor contributing to wave height, restricting waves in confined stretches such as lakes to small capillary waves or chop, while the greatest fetches, such as in the Pacific Ocean, produce much higher swell. Once the wave approaches coastal waters and the wave depth is less than 1/20th of the wavelength, it becomes a shallow water wave when bottom friction comes into play, as the orbiting water particles come into contact with the shallower seabed. This slows the bottom of the wave, causing the top to catch up and overspill, breaking on the shore. Refraction occurs as the change in speed causes the wave crest to bend toward areas where wave speed is slower in line with the topography of the seabed, and this orients the wave so it's parallel to the shoreline. As a result, when the wave breaks against a headland, it has a higher energy than when it arrives on a beach, and this influences coastal morphodynamics through erosion or by depositing sediment. Where a wave does not arrive parallel to the shore, this can result in longshore drift, redistributing the sediment along the coast. On the shore, the energy of waves is magnified by tidal influence, and in conjunction with weather patterns they can have huge effects on coastal environments, including storm surges and coastal flooding. Tides are effectively just the largest waves in terms of wavelength. However, they're not controlled by the wind but by the gravitational pull of the sun and moon, with the moon having a greater impact despite its smaller size due to its proximity to the Earth. The basic principle of this is that as the Earth rotates, its bodies of water are drawn toward the sun and moon, creating a bulge of water, but the rotation also creates a centrifugal effect, which produces a balancing bulge on the opposite side of the world. This effect is amplified when the sun and moon are in alignment, at full and new moons, resulting in higher tidal range known as a spring tide. However, when they're at right angles, the counteraction makes for a more even distribution of water with shallower neap tides. This basic description explains the underlying forces driving tidal patterns, but a combination of global topography, frictional drag and the obstruction of the continents brings other elements into effect, resulting in more of a swilling pattern in each basin. Just like with wind patterns, The Earth's rotation subjects the moving water to the deflection of the Coriolis effect. So as gravity brings the bulk of water at high tide back down the pressure gradient toward the centre of the basin, it's diverted to the right in the northern hemisphere, so a receding tide on the West European coast will move northwards towards Iceland rather than directly west. This continues in a circular pattern known as a rotary wave and works in conjunction with wind influence to contribute to ocean gyres, an example of which can be seen in the Azores high pressure zone above the North Atlantic, which in turn influences surface wind patterns across Europe. Because of the Coriolis effect, water in the middle of the basin builds up into a dome, and retreating downhill under the pressure gradient force is diverted again to the right, this time in a clockwise direction against the tide. In the southern hemisphere, meanwhile, the reverse is happening, and this results in gyres moving in opposite directions, bringing the westward flowing portions of the currents together in a mirror of the trade winds above. What has hopefully become apparent here is that not only do the physical processes within the ocean mirror the processes in the atmosphere, but they help to shape the global climate. From El Niño-induced weather patterns to the Azores high-pressure system, the oceans play as much of a part in regulating air temperature as the temperature-driven air density does in creating oceanic movements. And at the root of all of these interactions is the transfer of energy from the sun, the driving force behind all Earth's natural processes.